Now we're ready to start talking about Ampere's law, which is a way of finding magnetic field. We've already worked through the process where we found a magnetic field by doing an integration using the Biot-Savart law. But let's ask, is there an easier way to find a magnetic field in an area? So let's first start by remembering Gauss's law. So remember, Gauss's law says that the electric flux is given by integrating the electric field over an area, and it only depends on the charge inside the surface over which we integrate. So the net electric flux through a closed surface is the result of the charges enclosed by the surface only. So when we did this, this was an integral over a three-dimensional area or a volume, and the electric flux depended on the charge inside that volume. We were already able to find electric field of a continuous charge distribution by doing an integration over the object, but that can be a difficult process. Turns out using Gauss's law was a very quick and straightforward way to find an electric field, and we could only use it when there was symmetry. Ampere's law is analogous to Gauss's law. We find that the net magnetic field around any closed curve or any path, that's due to the total current within the closed curve. So as an equation, we would write that the integral, and it's over a closed path, so we write a little circle on our integral sign. So that indicates a closed path. The integral of the magnetic field over the path, so B dot ds, is equal to a constant, mu naught, that's the constant we've been using all along, times I with a subscript of in. I in means the current enclosed by that path. So now we're talking about integrating over a closed path, along a closed path. That means this is an integral in 2 dimensions. So that's another difference between Ampere's law and Gauss's law. So now using Ampere's law says that while we can find the magnetic field by doing an integration over an object, that's kind of a tedious way to do it. We can use Ampere's law instead to find the magnetic field as long as we have some symmetry. Let's start with an example of a long straight wire. We've already found the magnetic field around a long straight wire by doing an integral along the length of the wire. So that's a result we found already. Next, let's see if we can find it using Ampere's law. Remember, with Gauss's law, we had to pick a Gaussian surface. With Ampere's law, we have to pick a path. So let's ask, what path should we pick to find our magnetic field around the wire? So a good choice of path will be a circle, because a circle is easy to integrate over. The circle should cut through point P, because we'd like to find the magnetic field at point P, and we should have the wire at the center so that we have lots of symmetry. We also notice we have a dot product, so let's have the same orientation as our magnetic field for our path. So let's make sure our path and our magnetic field are in the same orientation. You notice when we have our Ampere's law, there is a scalar product here. That means our Ampere's law gives us the magnitude of our magnetic field. We still have to use our right-hand rule to find the direction. So you can't forget about the right-hand rule altogether. So let's draw our path on our picture. I've got 2 views. I've got a side view and a top view. Let's do the side view first. I'll label in that my current is going towards the top of the wire. So there's my current I. If you use your right-hand rule, you stick your thumb in your direction of current and your curled fingers show the magnetic field. So from in behind the wire, it's going to the left. swings out, moves to the right in front of the wire, goes down into the page at point P. Then we can draw our path. Okay, so that's what our path looks like on the side view. So there's our path S. For a top view, let's pretend that our eye is up at the top right here so that the current is coming towards us. So the current is out of the page towards us. Our path is still a circle around the wire where the wire is at the center and our circle cuts through point P. The orientation of that path is still with the circle. If you take your thumb and you stick it going towards yourself, you see that your fingers curl around in a counterclockwise direction. So that shows the direction of the path and the magnetic field. And at point P, the magnetic field would point straight up. Let's label that the radius of our circle is R. I'll label that in both pictures. Okay, next let's write down Ampere's law. The integral of B dot ds equals mu naught I in. Okay, let's talk about each of these things. We've chosen our path so that B and ds are parallel. That's to simplify our integral. Ampere's law is true no matter what path you pick. However, some paths would be more difficult than others. So if you pick the path where they're parallel, it's easy to do this integral. Let's deal with that part next. So the integral of B dot ds, let's put a ds on our picture so we're sure we know what we're talking about there. ds is a small part of the path. So I've identified it on the top view. It's a little bit harder to draw on the side view, but I'll give it a shot. So ds is just a little bit of that path. Okay, B dot ds is B times ds, magnitude of B times the magnitude of ds, times the cosine of the angle between them. I'll have to write tiny so I fit it in there. Hopefully you can still see it. The angle between B and ds, if they're parallel, is just 0. So I've got the integral of B times ds. B is a constant as long as we're a constant distance away. So B comes out front of your integral. The integral of ds is what we get when we add up the path all around the circle, and we get the circumference. There, I ran out of room, so I'm just going to write circumf for circumference, and that's equal to 2 pi r. So my integral of B dot ds is equal to B times 2 pi r. There's the left-hand side of our equation. The right-hand side is really easy to deal with. I in refers to how much current is inside that path S we drew. Well, the amount of current inside it is just I, the current on the wire. Okay, let's put it all together. The integral of B dot ds equals mu naught times I inside the path. The integral of B dot ds is B times 2 pi r. That's equal to mu naught times I. Solve for B. We get B is equal to mu naught times I over 2 pi r. So Ampere's law gives us the magnitude. We find the direction using the right-hand rule, and once we include the direction, we find it as a vector. So Ampere's law takes what was a very difficult integral problem and makes it a very straightforward problem. Let's do an example now that's just a little bit more complicated. Let's say that we have 3 long, thin insulated wires and they're very close together. We'd like to find the magnetic field 10 centimeters from those wires. So we have 3 currents. Current 1, I1, is 0.5 amps. That points straight up. Current I2, that's 0.75 amps. That's down. And current I3 is 1 amp. That one's in the back. That's 1 amp straight up. Let's write down our Ampere's law. Ampere's law says that the integral around some path of B dot ds equals mu naught times I in. where IN stands for the current inside our Amperian path. So whatever path I pick, and I'm not quite ready to commit yet, whatever path I pick, I'd like for it to enclose my 3 wires. So let's figure out what that current inside is before I fully commit to what my path is going to be. So my IN is my net current equals I1 plus I2 plus I3. Now current is a vector. I'm going to say upwards is positive and downwards is negative. So my net current then is going to be plus 0.5 minus 0.75 plus 1. There, I'm sacrificing significant digits for space on my page there. That gives me a net current of plus 0.75 amps. Because it's positive, it means that the net current overall flows upwards. All right, so now I have a net current flowing up. I'm going to choose my path to be a circle around my wires, and I'm going to choose that circle to be parallel with the direction that I think the magnetic field is. So my net current is up. I make a circle with my fingers. My thumb points up, and the direction of my field will be the same as the direction as it was on our previous slide. So the direction of our path will have the same direction. We'll start in back of the wire, and it'll come to the left. Then it comes around. As we come in front of the wire, it's going to the right. As we hit point P, the magnetic field goes into the page, and it comes around to the left as it goes behind the wire. If you prefer to look at the top view, you certainly can. So if we put our eye up here, then I1 comes towards us, I2 goes away from us, and I3 also comes towards us. I'll label those 1, 2, and 3. And then if we look at our path from this view, our net current flows out of the page towards us, so our path is going to come around in a counterclockwise direction. And our magnetic field at point P would point straight up because it's a tangent to the circle at point P. Okay, let's label the radius of our circle. So the radius R is going to come from the midpoint of those 3 wires. They're all really close together. So we neglect the size of the wires themselves. We should indicate a little bit of the path, ds. There's a small piece of that path. You can show it on both pictures, the 3D and the 2D. So we've already got our current inside. For our integral of B dot ds, I think I won't go through that whole process again. Since we did just do it on the previous slide, it'd probably be boring to watch again. But if this were a test problem, you would certainly show those steps. So I'll just write down show steps here. And after you showed the steps, you would see that you would get B times 2 pi r. So now we'll solve for our magnetic field. B times 2 pi r, that's the integral of B dot ds, is equal to mu times the net current inside, which we found was 0.75 amps. So we can solve for our magnetic field. It's mu naught. Why don't we just fill in the value for mu naught here? So that's 4 pi times 10 to the minus 7 Teslas times meters over amps times our current inside, 0.75 amps, divided by 2 pi times how far away we are. That's our r, which is 0.10 meters. So what we get for our B then is 1.5 times 10 to the minus 6 Teslas, and the direction in our side view would be into the page. and that's a vector. Again, we get our direction using the right-hand rule. Here's an example I grabbed from the Young and Friedman textbook. So I've got 3 current carrying wires and I've got 4 different paths, and the question asks, what is the line integral? What is the integral of B dot ds for every path? Now, one important thing to deal with is what it says right here. Each integral involves going around the path in a clockwise direction. So let's put that in context and make sure we know what that's telling us. Ampere's law says that the integral of B dot ds is equal to mu naught times I inside the closed path. Our scalar product here, B dot ds, means that we need to worry about orientation. The sign convention matters. So what we know is if B and ds are parallel, that will give the integral of B dot ds positive. And if B and ds are antiparallel, don't know exactly what's the right sign for antiparallel, so I'll just write out the words. So if they're in exactly opposite directions, then the integral of B dot ds is negative. So when B and ds are in the same direction, it'll be positive, opposite directions be negative. If the integral of B dot ds is positive, the current is positive. If the integral of B dot ds is negative, the current is negative. So it says that the integral involves going around the path in a counterclockwise direction. So any path will have a direction like this. So there's our S, and a little bit of that path would be ds. So in order for that integral to be positive, the magnetic field would also have to go around in the same sensation, B. Now we'll apply our right-hand rule. So you take your right hand, and you do this along with me. Take your right hand, you curl your fingers in the orientation of B. So make your fingers in a circle that are coming around counterclockwise. What is your thumb doing? It should be pointing straight at your face. So that means if your B goes around in a counterclockwise orientation, your wire is coming out of the page. So in this case, B and ds are parallel. So our integral of B dot ds is positive. Therefore, our convention is that currents which point out of the page are positive. So it's important to read every little bit of a problem before you get started. Now that we've got our convention settled, we'll go ahead and solve our problem. So let's deal with each path. So for path A, the integral of B dot ds is equal to mu naught times I in. I in refers to how much current is inside path A. If you look at path A, there's no current inside there at all. That's 0. Okay, so part A was pretty easy. Let's do part B next. So part B, the integral of B dot ds equals mu naught times I in. Let's look at the current that's inside our path B. So path B has current I1 in it. Current I1 points into the page. That's opposite of our convention that says positive current is out. So current I1 must be negative. So minus 4 amps. Mu naught, I'm not going to fill in that number. I'll just write it down here at the bottom. Mu naught is 4 pi times 10 to the minus 7 Teslas meters over amps. So we'll take that number, we'll multiply it by negative 4, and what we get for our line integral then is minus 5.03 times 10 to the minus 6 Teslas times meters. Okay, next we get to part C. So same deal, integral of B dot ds equals mu naught times I inside. So here's our path C. The current inside is I1, which is into the page, that's negative, plus I2, which is out of the page, that's positive. So I've got mu naught times minus 4 amps, that's our I1, plus I2, which is 6 amps. Minus 4 plus 6 gives us 2. We multiply that by mu naught and we get positive 2.51 times 10 to the minus 6 Teslas times meters. Okay, last we have path D, integral of B dot ds equals mu naught times I inside equals mu naught. When we look at path D, we have current I1, current I2, and current I3 inside of path D. So we've got minus 4 amps plus 6 amps plus 2 amps. Sum of that is going to give us plus 4 amps. Multiply that by U naught and we get positive 5.03 times 10 to the minus 6 Teslas times meters. Okay, so that was kind of a good problem, and hopefully it showed how important it is to get your sign convention correct.